or else, yeah, it was awful.
Yeah, that's why I started wearing
Baby shark
around, walking around.
drove me nuts. All right, last set of notes. We start today. We may finish today. We may finish tomorrow. It just depends on how fast we can get through them, okay? The last part of the notes is talking, I think you may have asked me about electroplating. So we end up talking about that. We end up talking about corrosion, and some of that you can kind of read on your own because it doesn't pertain to the test, but it's just interesting to kind of know. All right, voltaic cells. Voltaic cells at non-standard conditions. Okay, Le Chatelier's principle can be applied to that. An increase in the concentration of the reactant will favor the forward reaction, and the cell potential will increase, and then the reverse is also true. So if we look at this, we can see, here we go. Okay, we can look at these and we can see which one of these protect whether E cell is larger or smaller than E not cell. So this is standard conditions for the solid cases. So we need to talk about what standard conditions are. We talked about this several times, but we're going to talk again. Remember that E naught is temperature is 298. The temperature is 298. It's a 1 molar solution. So down here, we're going to change the molarity of these solutions. And it is 1 atmosphere pressure, okay, which is typical pressure at sea level, okay? And then everybody else is a little different. Depends, it varies a little bit based on weather fronts that are coming through as well. But that's all earth science, and yeah.
We'll stay chemistry.
Okay, that's good. I don't want to teach earth science anyway. I'm certified, but I don't want to do it. All right. If you look up these potentials on that chart, which I'm sure you've gotten pretty comfortable doing now, so I'm not going to flip up to the chart. Oh, I forgot. This won't let me write on here anymore. But I'm not bitter about it at all.
Did you start the recording video?
I did.
Okay.
I did do that at least. All right, let's try this again. If you look this up on the reaction potentials, you will see that this has a negative 1.66, and my manganese here is going to be a negative 1.18. Okay, I had to pay attention when I was looking these up. I saw that this aluminum was losing 3 electrons, and I saw that this manganese was gaining 2 electrons. So if we wanted to, we could go through and we could balance this redox reaction. To answer this question, we don't need to, but we do need these values. And I needed to make sure that when I picked them out of the table that I used the appropriate ones. Okay? Because manganese can lose or gain, or can lose a bunch of electrons. It can lose up to 7. So, or gain, yeah, gain, anyway. So we need to identify which one of these is reduced and which one of these is oxidized.
I was going to say Alabama, but it's aluminum.
Aluminum is what?
Reduction.
Really?
No,
It's more. Oh no, I was thinking that
This,
1.8.
which one is closest to 0? This one is. This one's furthest away. These are both negative values. So that means that this one's reduced.
Yes.
And this one's oxidized.
I thought it said 188, not 118.
It's negative and
Well,
negative.
That too. I know it's
Okay.
negative.
All right. I'll show. Okay.
I just was reading it, buddy.
All right. So if we look at these reactions, right? These were at 1 molar. Everything was at 1 molar if we're at E cell. Okay. And we've taken our aluminum and we've made it 2 molar now. So it's not at standard conditions. Which way is this reaction going to run? This is at 1 molar. This is at 1 molar. This is at 1 molar. Well, Le Chatelier, this wants to balance out. What's it going to do?
It's going to create more problems.
Right. It's going to shift to the right. Okay, so we're going to shift to the right. So remember, when we're figuring out our voltage, we do cathode minus anode, right? This is going to get cathode value is lower. Cathode value is lower. My cathode. Oh crap! I screwed that up. That's why. Because read the problem.
Oh, you're increasing the aluminum.
Yep, I screwed up. I'm sorry, guys. I'm so sorry. This is still 1.0. This is 2.0. So this is not going to shift to the right. It's going to shift to the left. Okay, now that makes more sense with what I have down in my notes. So this amount, we're going to shift this direction instead of shifting it this direction. So this means that the E cell is going to be less than the E cell not. Because we've shifted it, we're going backward essentially. Okay? So the forward reaction would give us an increase in this value. Remember, because the answer here, if we subtract it, if we did our C minus A, we get 0.48 volts. But now we're backing it up. We're backing that train up. That makes sense? So going forward, it's going to give us this. But now we're taking some of this and going and reversing it. So it's kind of interfering a little bit with this. That makes sense? It wants to go this direction, right? It wants to take this stuff and reduce it and go to this direction. This is the way the reaction wants to proceed. But now we've added this stuff in, so it's going to back it up this direction. So it's essentially going like this, but now we have some kind of interference that's going to push it, some of it back that way. Okay? All right, now, if we look at the counter of that, or the next situation, I guess. Here, we are taking this guy, Mn3+, so this is going to be 3 molar. These are 1 molar, which are standard conditions. And now, normally it wants to be this way. Now, which way is the reaction? Well, it's going to shift to the right. So now we're kind of adding to this. It's almost like a vector thing in physics. You're adding it. So it ends up being the opposite effect. Okay? So this direction, when we carry it this direction, we're actually going to be making more electrons this way by increasing that molarity. All right. Then she talks about the Nernst equation. They have a rearranged version of this, and I did not include it in your stuff. If you get into college, your professor might give you this rearranged version where they actually do some of this gas constant divided by Faraday's, you get a number. If you want to memorize that and figure it out on your own, that's fine. But since this isn't on your constant sheet, I didn't want to talk about this. So I pulled it out of your notes. This is the Nernst equation. This is on your blue sheet. And this is one of the final equations that we're going to talk about. We got this one and I think one more, and we've covered every equation on that sheet. Did you ever believe at the beginning of the year that you guys would get through all? I mean, that's a lot of equations, It's kind of cool.
I knew that would, and I was terrified for it.
But it's not been that bad, has it?
Debatable.
Okay.
I haven't cried yet. This unit.
So if you are at non-standard conditions, this E naught is equal to negative RT over N, and remember that's the number of electrons, times your Faraday's constant, times the natural log of Q. That's why I don't like, in the old way of doing this, when we had big ideas, they would talk about this, but at that point we hadn't taught equilibrium yet, so nobody knew what Q was. So that's why I like the way this is set up now. All right, so eventually E will decline to where it reaches 0. When E is at 0, you have a dead battery. In this situation, Q is equal to K and delta G is equal to 0. So at delta G equals 0, you got a dead battery. Q equals K in this situation, you got a dead battery. All right. We can construct cells where both compartments contain the same components, but at different concentrations. So here, and we just talked about that up above here, how we could use that to generate electricity. If you have the stuff over here at higher concentrations than the stuff over here, it's going to drive, it's going to provide a driving force to get to this side. Okay, so you can have a situation where you've got these over here, this component has different concentrations than this component. All right, so here we're going to determine the flow of our electrons. All right, so notice that, well, let me get this snipped so I can work with it. All right. So we need to figure out what is our cathode and what is our anode. So we can look at our potentials. Well, no. Yeah, this is 0.01 and this is 0.1. Okay. So our cathode is this side here. And this is going to be our anode. And how do I know that? Well, let's talk about that, okay? If I have electrons that are flowing through here, okay, they're going to flow yeah, that makes sense. Okay, sorry, I had to like wrap my brain around it. It wants to get these concentrations equal to one another, right? You follow that? This concentration is much higher than this concentration, yes? If I take these Fe2 plus and I add 2 electrons to it, I'm going to be making Fe here, right? And this guy's going to get bigger. And that's going to reduce the concentration of Fe2 plus in here and get it closer to this. In order to do that, though, I have to take electrons. I'm going to increase the Fe2 plus here by taking 2 electrons away from this, sending it across the wire. It's going to grab those 2 electrons. It's going to grab up some iron and deposit it on here and make this bigger. So how did I know this is the cathode then?
It's getting bigger.
Exactly. Exactly. This is getting bigger. Remember your fat cat? Okay. So because this is getting bigger, and then as that gets bigger, this concentration is going to diminish because we're adding those in. This concentration is going to increase because we're adding in 2 plus ions here as the electrons are coming up. Does that make sense? So they asked, which direction do the electrons flow? They're going to flow this direction. So fat cat is from anode to cathode. Or I always think about it as the cat's getting bigger. All right, everybody cool with that one? Good with my explanation? Does it make sense, I hope? I got too many things open here. All right. Ready for some fun?
No.
Oh, yeah.
All righty. You should see my notes. We are determining E cell prime and E cell based on the following half reactions. Okay? E cell prime is easy. We just simply use our math here. Okay? Which one's our cathode? Which one's our anode?
Cathode is bottom one because it's more.
The what is?
It's the zinc one.
The zinc is what?
Cathode.
Nope.
Less positive. Oh, wait. It's more positive. It's more positive.
More positive is your cathode,
Yes. Yeah, the top.
and this is your anode. So we are going to go, remember, to figure this out, we go Ka. So E prime equals Ka. Yeah, sitting in the exam, Lippy's kids go Ka. Everybody looks around like, what? Minus a negative 0.76 volts. So E prime, you better be able to do that one in your head. 1.76 volts is my E prime value. That's easy. You should be able to do that in your sleep by now.
Oh, yeah.
Why do I feel like this is like
What?
more annoying?
Can't hear you through that mask. What?
Why do I feel like this is going to get much more annoying for them?
Yeah, we got to figure out E cell now. Okay. So when we do that, we've got to balance this half reaction. Okay. Without having to rewrite this whole thing, to kind of spot and see how many electrons you're going to have, can you look and see what the least common multiple is between these? 2. So we could sit here and we could flip this guy around and we could put stuff, we could go through and we could write the extra coefficients on here. So this would be a 2 and this would be a 4 and this would be a 2 and this would be a 2 and this would be a 2. But we need to save time on this exam. So if you can look at this and figure out what the least common multiple is and get n equals 2 here, that's going to save you some time. All right. I don't like cutting corners, but we need to find some spots where we can. And I think that this is a comfortable spot to do so with. Okay. But we're going to need that because this is going to be our equation. E cell equals E prime, which we have right here, minus RT over NF, and we just figured out N right here, times the natural log of Q. Oh, maybe we did have to do that. All right, we're back on the train up. Can I just re-record this?
Go for it.
The N is still valid. That's still a valid thing. But the problem is that we've got to figure out the actual equation. We've got to sit here and flip that guy around because if we don't, we're not going to be able to figure out our LQ thing here. Oh, Lippy, trying to cut corners. So disappointing. Okay, so this one's getting reduced and this one's getting oxidized. So he's going to lose electrons. He's going to gain my electrons. So I need to flip him around. Does that make sense? I got to flip this guy around. I have to flip him around because he's gaining the electrons that this guy is losing. Okay. So Zn, make sure I'm writing that down right. No, I'm not doing that right. He's losing his electrons so he can gain them. So I got to flip this one around. I'm sorry. I got to flip this guy around so this guy can gain them. So I'm flipping him around. Flip around. And I'll explain why in just a second when I get it flipped. Okay. So Zn yields Zn 2 plus 2 electrons. He is going to lose 2 electrons, and he's going to become this guy, and those 2 electrons are going to come over here, and they're going to get picked up right here. I'm sorry. I've screwed you guys up majorly today, and I apologize for that. Plus, now I'm going to go ahead and multiply all this stuff out by 4 or by 2 while I'm doing this.
So you always flip the reduction one because that reduction is gain?
No, I'm flipping the oxidation one. That's the one I've got to flip. I flipped this guy around. Do you see how I flipped him around?
Why are you switching that?
I'm not switching this one. I just forgot to put my plus there. Right? No, I did have my plus there. I did have my plus there. I put it there again. So that is this. I just doubled it because I needed these 2 electrons. That's this guy. I doubled him. I doubled him. I doubled him. And I doubled him. And I had to double them because I need to get rid of these electrons. Good. Okay, now I can rewrite this as 2VO plus 2 plus 4H plus Zn yields Zn2 plus 2VO2 plus 2H2O. All right, you ready?
Oh, yeah.
Everybody? Got all that written down? Okay. So we start plugging stuff in now. Our E cell is going to be equal to, we calculated that right here. So that is 1.76 minus R. Now, on your sheet, you have 3 different R values for constants. Okay? You have one that looks like this, which is 8.314 joule mole K minus. You've got another one that's 0.8206, and that is liters atmosphere mole Kelvin. And then you have another one that is 62.36 liter torr per mole Kelvin. Okay, so you've got to figure out which R value here you want to use. Well, this one is the only one that has joules in it. And remember, Faraday's constant has those coulombs per moles of electron, okay, which has a component of joules in it. So this is the R value that we're going to want to pick to work with this. So that's what I'm going to use for this. And I just wanted to explain to you how I figured that out. 8.314. My temperature is here, but what do I have to do? Right. So that's 298 Kelvin. over, how many electrons did I need to use?
2.
2 times Faraday's constant, which is on your sheet, 96485. Now, that would be lovely if we were done with this, but we're not. We have to figure out the natural log of Q. So we've got to figure out Q here. How do we do Q?
It's 1.00 or on the right track?
Yeah.
1.00 times 10 to the negative 14.
No.
No,
No.
not at all then.
No. Remember, Q is a ratio of your products raised to their coefficients divided by the reactants raised to their coefficients, and then you multiply everything together. So they gave us the concentrations over here. We just need to, and this is why I had to go through and balance this sucker, because I was going to need these coefficient values here. Okay? That's why I had to back my train up, admit for the 15th time today that I screwed up. It's been one of those days, you guys. All right, so I am going to figure this out. Well, this is a reactant here. So this is one of my reactants. No, this is not one of my reactants. This is a product. This is one of my products right here. Product, okay? So that's going to go on the top line. This is going to be a product. And I am going to raise that product to the second power. Okay, so he's going to go up to the 2. I also have, this is a product, zinc, okay? And he is going to be a product, and he doesn't get raised to anything because he's just got a 1 here. Now, remember, for these equations, we don't count water in that Q value. This is in what state? See it right here? What state is that in? Solid, liquid, gas? Solid. We don't put solids in this thing either. Okay? So we don't need to account for him, and we don't need to account for him in this reaction quotient. So I'm going to take this value, 1.0 times 10 to the minus 2. That is this one. I'm going to raise that to the second power because of this coefficient. Then I'm going to put my value in for my zinc here, which is 1.0 times 10 to the minus 1. And I'm not raising him to anything because he doesn't have a coefficient here. Now I need to put this guy and this guy in. So this guy is 2, and I'm going to raise him to the second power, times 0.5, and what am I raising him to? The fourth power, because of his coefficient here is a 4. All right. Once you're done with that, then you need to find the natural log of this. You need to multiply all of this stuff out. Then you need to subtract that whole blasted thing from 1.76 to figure out E cell. See if you can come up with 1.89 on your calculator. I didn't the first time, and then I realized, banged my head, I realized I didn't take the natural log of that reaction quotient. Had to go back and do the thing again. And that's a long string of numbers to put in a calculator, let me tell you. Mr. Stookie sent me a recipe for brown butter bourbon pecan chocolate chunk cookies. He brought some in the other day. Oh, they were so good. I had 2. I was a little piggy. Oink, oink. And see if you can get your calculator to be friendly to you and give you the 1.89 volts that it should. Wasn't that fun? That was so much kinds of fun.
Yeah, my calculator doesn't like it.
Okay, so for this, what I ended up doing was this top line here. When I calculated that out, I got 1 times 10 to the negative 5. Did you get that for this top line?
For which one?
The top of this part of the reaction quotient.
Yeah.
And then I got 0.125 for down here.
No. I got 0.25.
1.25 or 0.125.
No, just point.
Okay, do 4 times and then 5 raised to the 4th power. 0.5 raised to the 4th power is what?
0.25
Yeah, so that's
4.
0.5 raised to the 4th times 4. It's 0.25. Oh, yeah, I guess it is 0.25. Huh. All right, Austin's right, I'm wrong. Yeah. All right, take the natural, divide these things out and take the natural log of that. I got to go up here because I ran out of room. Yep, there you go.
I did it.
What?
Wow.
What
I
did
have
you
no
get for your
clue how I did that, but I did it.
natural log to
I ended up with natural log of 8 times 10 to the minus 5 times 0.0128 minus and then 1.76.
Wait, for what? Okay.
I don't know what I keep doing wrong. Oh my.
That's not your.
I've been clicking log.
Natural log, honey.
I know.
Okay.
For the natural log,
Oh
I
my
had
God.
4 times 10 to the negative 5.
Well, this is you have to take the natural log of this. I haven't done that yet.
Yeah, I know, but like at that point, too, before taking the natural log, I had 4 times 10 to the negative 5.
Okay. So maybe I'm off here because I have my 0.25. So at any rate, you should end up with 1.89.
It did have that.
Good. All right. Moving on. You ready to move on?
Yes.
All right, so that takes care of that. Now, here is something that is important about this, okay? If your E cell comes out to a negative value here, then it's not spontaneous.
No, I keep getting a negative.
We'll have to sit and play with your calculator, okay? If E cell, or if E prime is positive, that means that it's spontaneous. That's going to make a good battery. If E cell equals 0, equilibrium has been reached and you've got a dead battery. The larger the voltage, the more spontaneous the reaction. Delta G will be negative in spontaneous reactions, and K greater than 1 is favored, because that means that you're going to make more products than reactants. These are 2 really important reactions. Now notice, or equations, notice that both of these are equal to delta G.
Mm-hmm.
If A equals B and B equals C, then exactly. And you can use this for a lot of stuff, guys. Okay? That's what's really cool about this, is you can take this and you can go NFE prime equals Ratlink.
I figured out what I was doing wrong.
Okay,
I
good.
wasn't following 10 tabs. So.
people with calculators, as smart as they are, they can't follow numbers. It's annoying.
You mean your calculator can't like think? It's not capable of that? It follows orders of operations because that's the way it's been programmed and it doesn't have a cognitive ability to think? Yeah, it's a calculator.
We learned it from first grade.
On your sheet, I wrote this for you. Okay? Because this is important. It's important to see that these things equal in one another. This can get you out of some sticky situations. Gibbs free energy is G. Spontaneous or thermodynamically favorable when delta G is negative. Faraday's constant then, and your number of electrons. E is your cell potential. R, you're always going to want to use this because this has joules in it, and that gets rid of these joules. So use this guy to get rid of that guy. Kelvin is your temperature, and remember how to do an equilibrium constant. Okay?
So are we gonna have any like 9-point any workers like what's in here left?
That's what's left, and then we start our review. I have given you your final sheets of paper, and I guess by you packing up right now, we're done, or?
Well, the next one's finished.
Oh, okay. So you don't want me to do it today? Want me to hold that one off till tomorrow?
Let's do number 8.
I am getting through these tomorrow, I'm telling you. I am not going to continue notes on Monday, so.
It wasn't my calculator.
You be ready.
It was me not following PEMDAS. Or PEMDAS.
All right, I will quit, but I'm not going to quit tomorrow. I'm going to keep plugging through, and whatever I don't cover, like I'm going into 7th hour and you can listen to the lecture. Well, you guys won't be here, but the kids tomorrow, I'm telling you, I'm not going to lecture next week. I'm done lecturing after today.
Oh yeah, I know you've been getting so used to in classroom every day, in the Google Meet.